Well, as a further example of centripetal force, let's work out a situation where we're riding on a Ferris wheel, a big vertical wheel with seats on it that people get in and ride around the wheel as it spins relatively slowly. But let's see what the contact force is with the seat is on a passenger, both at the top of the Ferris wheel and at the bottom of the Ferris wheel. Of course, we should start with some drawings that indicate the forces that are present, the accelerations that are present, as we seek to do this calculation. At the top of the ride, there is a weight downward on this individual, and I'm not seeing it here, so I'm going to go ahead and draw that in. But there's mg acting downward on this individual, and there's normal force going upward on the individual. Do these two forces add to zero? Normal force upward and mg downward. Do these two forces add to zero? The answer is no. We need a centripetal force. We need a net force towards the center of the circle to make this person go around in circular motion. We need a net force towards the center. So the subtraction of these two forces will provide the centripetal force. The subtraction of normal force and mg will provide the centripetal force. At the bottom, normal force, the seat is pushing upward again, the weight is pushing downward. We need a net force towards the center, and in this situation the normal force will dominate over mg, and we need this inward force. At the top, the mg is going to be the larger force because we need a net force towards the center of the circle. So we have that background, and some of the parameters here. The mass of the person is 80 kilograms. The radius for this particular Ferris wheel is 8 meters, roughly 24 feet. We're going to let the Ferris wheel go around once every 15 seconds, one revolution every 15 seconds. Well, we can find the velocity, the magnitude of the velocity. The person goes around a circle. The circumference of the circle is 2 pi r, so 2 pi times the 8 meters divided by 15 seconds. That provides us with 3.35 meters per second, the velocity. We need that velocity because we need the centripetal acceleration in order to work with centripetal force. So v squared over r, I'm calculating that here. I square the velocity, I divide by 8 meters, and we get 1.4 meters per second squared. When we square the 3.35, we also square the units, so meters squared divided by second squared, and now we divide by the meters, so one factor of meters cancels, and as we should, we have units of acceleration. The centripetal acceleration is 1.4 meters per second squared. So at the top of the ride, taking up to be the positive direction, we have normal force going upward. The mg is downward, so when we add the forces together, that brings in a minus sign. These two forces oppose each other in terms of the motion of the object. Normal force is upward, the weight, mg, is downward. And here's something to be careful of. What's the direction of the centripetal acceleration? The centripetal acceleration is downward. So we have to bring in a minus sign for the centripetal acceleration. So the ma over here, it's a minus mv squared over r. And putting in some numbers, 80 kilograms for the person, 9.8 of course near the Earth. We have 80 kilograms again, and here minus 1.4 meters per second squared. You should do this on your own calculator. I don't know what was scribbled out here, but I came up with a better value. I must have mispushed some button. But 784 here has to be added to both sides because the centripetal acceleration is a negative quantity. It's in the down direction. On the right side, we have minus 112, and the net of these is 672. Does this make sense? Here's the weight of the person, 784. The normal force, 672. So we're going to have more force down, the weight, compared to the upward force of the seat. So let's take a look now at what happens at the bottom of our motion here. We have a little change in the direction at the bottom of the circle. again, the same basic quantity. Normal force upward minus the weight is downward. But now the centripetal acceleration is upward. So we bring in the 1.4 value of centripetal acceleration as a positive quantity in our calculation. And that leads to more force than the weight, 784 plus 112. At the bottom of the ride, the seat pushes up on the person with 896 newtons. So you'll get a slight sensation on this on a Ferris wheel ride. You kind of sink deeper into the seat at the bottom. Your stomach kind of flutters at the top. There's less contact force between you and the seat. And there's what you pay the money for, and a good view at the top of the ride. So keep practicing, ask questions.